Okay, so did you have a chance to visit and to try to draw these out? Okay, well, let's take a look at them together, and you look at your structure and you kind of compare mine. Okay, so this one is hydrogen, and hydrogen needs 1 electron, but there are 2, so 2. Oh, I'm still in yellow, and you can't see that, I'm sure. Let's go back to black. Okay, because I can't see it. Okay, so there are 2 of them, and each one of them has, there's just 1, so we need 2 valence electrons. So we're going to have a hydrogen bonded to a hydrogen. Ta-da! That's about it. That's all you got. Okay, so the next one is going to be boron trihydrate, or trihydride rather, and this is kind of one of those weird little exceptions. Boron's kind of needy to a certain extent, or he has high expectations. Because he's only going to form 6. He won't have a full valence shell, so he's going to only form 6. So his behavior is very strange. Okay, so he's in group 3, and there's a hydrogen, and so there are 3 of them, and each of them have 1 valence electron. So that's going to give me 6 valence electrons. Okay, so let's draw boron. So there's boron, and there's a hydrogen, and there's a hydrogen, and there's a hydrogen. Ah, there it is. So 2, 4, 6. So this is that situation where boron's not going to form an octet. Like, he's not going to do that classic 8. He can, but like I said, he's very needy, and we'll talk about that a little bit later. I need you to be comfortable with drawing the structures first. Okay, so methane, we did methane. Let's take a look at that one again. So carbon is 4, and hydrogen has 1 valence electron, but there are 4 of them. So, of course, that's going to be 8 valence electrons. And so you have carbon, and then you have your hydrogens. Okay, very good. And then we have water. So water, there are 2 hydrogens, and each of those hydrogens has 1, and then oxygen is in group 6. And so that's going to give me 8 valence electrons. So if you haven't already, make sure you've got your periodic table ready, because you can't really draw it without them. So here's our oxygen. There are the hydrogens. Okay, now, so we need 8 of them, right? So here I have 2, 4. The hydrogen can't hold any more electrons. So the only other place that I have available is around the oxygen. So let's put some dots around oxygen, just like we did earlier with C2H2. So there are dots. So 2, 4, 6, 8. Who do we appreciate? We appreciate water. Okay, and then last but not least is hydrogen fluoride. And so, of course, hydrogen has 1, fluorine has 7, and this is going to give us 8 valence electrons. So you have hydrogen bonded to fluorine. Okay, so that's 2. So I need 6 more. The only other place that I could put them or place them is around the fluorine. So 2, 4, 6. Okay. All right, so that takes care of our molecules. I hope that you were able to draw them. And it's okay if they don't look exactly like mine. Remember, I just think symmetry, and I've been doing this for a number of years, and so I'm falling into some habits. Okay, so on this side of the page, it says, based on the Lewis structures, what do you think is the proper formula and Lewis structure for H sub x, where x is the number of hydrogens? Okay, so here comes the thing of how do you know where the subscripts come from? And that, again, is going to be based on their group number. If you guys will remember, nitrogen is in group 5. But he's only going to really need like 3 more of those electrons. So that's where this comes into. That's like ammonia. Yeah, you guys probably have cleaned this in ammonia. So that's NH3, and so that's how it's dictated. And you remember when nomenclature, when we were looking at the group numbers, and the group numbers were telling us how many electrons were going to be shared or how many electrons were going to be given, it gets kind of strange when you're looking at covalent compounds. So like for silicon needs 4, so of course X will be 4. Hydrogen only needs 1, and bromine can only give 1, so X will be 1. And then I think this is supposed to be a hydrogen, I'm not sure what happened. And so sulfur's in group 6, but he needs 2 more, so it would be H2S. And this is just, again, to get you thinking about the relationship between group numbers and the numbers of electrons that need to be given, taken, or shared. So why is the formula for H2O instead of H4O? Why is it BH3 instead of BH4? Well, it's all about their capacity for electrons. They only take what they need. If you had H4O, this would create a charged substance. So a charged substance. Folks, charged substances are not stable. So the whole reason that elements will form compounds, or that compounds even exist in the first place, is to become stable, is to reduce the charge and become stable. So, so making Lewis structures, we need to really think about making them stable and reducing the charge. Okay, so here are some that are for you to practice with. They're going to be kind of difficult. I already have this one done for you, and it was just kind of illustrative to show that you have a nitrogen and have 2 hydrogens. Remember, hydrogen is going to always be on the outside, and then the nitrogen will be in the middle bonded to oxygen, and of course this hydrogen. So a lot of times the compound is going to tell you what the connections are in space. The other object, or other one that I wanted to kind of look at, were these charged species. So if you remember, in nomenclature we learned about polyatomic ions. And polyatomic ions are going to have charges, and really trying to understand where those charges come from. And so I thought we could look at one of those this evening. So let's look at ASO3. That one just looks way terrifying. So let's go ahead and look at this one together. And then for homework, this is going to be your assignment, is that I want you to try to draw these. Now when you draw these, you're going to be doing this on paper. And you're going to have to take a picture of your homework, and that's what you're going to upload into Moodle, and I'll have all of that stuff set up. It will be later on this evening for you, and even into maybe Thursday. But you're going to upload this stuff and just show me how amazing you are at drawing Lewis structures. This really is just for fun. This is not meant to be necessarily right and wrong. Just looking to check to make sure that you followed the rules and that you've tried this. So it gives us a really sincere appreciation for the shapes of molecules. But let's take a look at this charged molecule first. So we've got arsenic and oxygen. I think this is arsenic. So it's a polyatomic ion. And arsenic, I'm looking on the periodic table. He's in group 5. So he needs 5. Ooh, that's not going to help us. He needs 5 valence electrons. Let's do white. Okay. So he needs 5 of those. And then oxygen is in group 6, and there are 3 of them. Okay, now this negative means that they need to gain 3 electrons. So let's say plus 3. So therefore, if it was positive, you would have to take away 3. Remember, a negative means we gain 3 electrons, or we gain that number of electrons. Positive means we would subtract. Okay, so we got 5 plus 18. And 5 plus 18 is what, 23? And then plus 3 more gives us a sexy even number. So 26 valence electrons. Working with odd numbers and electrons is really weird because they're supposed to be paired up. So it makes it difficult. So let me just check my math, make sure. So we got 6 times 3 is 18, plus 5 is 23, plus 3 is 26. Excellent. Okay, so since I have 1 arsenic and I have 3 oxygens, I'm going to put arsenic in the middle. Okay, so arsenic goes in the middle, and then I'm going to put the oxygens around him. So let's just do this. And I'm going to erase this because I don't remember what that is. I don't know what happened. So it was probably something I did. So, all right, so there's oxygen. So we've got oxygens around him. Okay, so let's go ahead and put some electrons around oxygen. Remember, we got to find homes for 26 of these puppies. So I'm going to do dots. We've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 23. Okay, but, 24, excuse me. So let me count again. So we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Yes, yes, yes. And so I need 26. So the only other logical place that I could put them, of course, is around arsenic. So I'm going to put them right here. Okay. So the dots represent electrons that belong to that atom. Lines are going to represent electrons that are being shared. Let me darken this up just a little bit. This is looking pretty good on the screen. Okay, now there's this thing called negative charge, -3 charge, and I can't ignore that. So I think the best way to understand this is something called formal charge. Formal charge is once minus has. Okay, now he wants this many electrons, and that's based on his valence shell. And what he has is what is around the atom. So around the atom. Okay, kind of like around the horn. All right, so once is the valence number of electrons. So that's the stuff that comes from the periodic table. And then has is the stuff that we're counting around them. So let's take a look at these oxygens first. This is going to be the easiest one for you to see. Okay, now remember, oxygen wants 6 electrons because he's in group 6. So this oxygen has 2, 4, 6, 7. Now remember, he only owns one of those electrons. Arsenic owns the other one. So 2, 4, 6, 7. So then you have 6 minus 7 is a -1. So that means that each one of these oxygens is going to carry this -1 charge. Okay, so 6 minus 7 equals -1, and that's on each one of them. Well, we're in business because 3 times -1, -3. Yes? Excuse me. Yes. Oh, I hope I said that right. Anyway, I think you know what I'm trying to say. All right, so let's look at arsenic. Now, arsenic is, he's in group 5. That's what we established here. So let's count 2, 3, 4, 5. Remember, he only owns one of these electrons. So 2, 3, 4, 5. He wants 5. He has 5. So he has no charge. And that is a perfect scenario. If you have to put a charge on an atom, you want to make sure it's on oxygen. Okay? Because he's highly electronegative. He's really close to fluorine. He's kind of small. I mean, he's going to really want to carry that negative charge. He's going to want those electrons. So this is a perfect scenario for us. And of course, I'm going to put this in brackets, and I'm going to show that the whole thing encompasses a -3 charge, that it's for the whole ion. So I want you guys to try this, these at home, and practice calculating formal charge. You're really going to need it with this one. But just take a bash at it, see what you can do, and upload your homework when you get done. I can't wait to see it. Take care.